Greetings. Welcome back to AP Physics C Mechanics, where we're covering Unit 4 over momentum and impulse. And in this video, Chapter 2, we're going to be covering the namesake of the unit, momentum and impulse. But before that, I wanted to cover a little bit of history or background over exactly how we got to momentum as a quantity. Because sometimes it can feel like it doesn't really have a place in a world where we already have a pretty good understanding of velocity and mass and force and even energy to some extent. Now, if you want to skip over this history stuff, it is not crucial to your understanding of the topic, but it does give a better idea of exactly where momentum is coming from and some of the uses that we apply it to. But if you want to skip ahead, I'd say in the time bar below, just skip to momentum and Newton's second law. Now, I'm starting very early with the background on this, with Aristotle, which is like early antiquity. And Aristotle was a Greek philosopher known for many things outside of his works on physics, who helped to pioneer a lot of the foundations that we use today. He did a lot of work on a written work titled Physics, which covered a lot more than what you would generally consider to be physics today. It was just kind of a general scientific philosophical work. Now, Aristotle, in his contributions, first tried to come up with some explanation for how objects moved, just in the simplest way possible. Aristotle stated that everything that is in motion must be moved by something, or a mover. Now, Aristotle defined motion as two different things. He classified them in two different ways. An object would have natural or internal motion, which he observed that objects would naturally sink or float, or they would naturally fall to the ground if you dropped them. Therefore, that motion must be moved internally. That is a force that is pushing the object from within. If either of those two situations are not at play, then the object's natural state is to be at rest. Now, unnatural motion, really the other type, was defined as violent motion. And this was something that had to be caused by some kind of physical mover that would be applying this force that is not natural. That could be anything from like the hand of someone throwing a rock. It could be air, it could be a bowstring, really anything that you would consider to be able to apply a force. This would be the cause of a violent force. And that theory was all well and good. It did at least a decent job of explaining how things moved. It makes sense that you would think something has to be pushing something in order to move it. But there was a bit of a problem with that, which is that if you take Aristotle's theory at face value, then it doesn't do such a great job at explaining exactly what happens after something leaves a mover's hand. Like, say somebody tries to throw a rock. Well, if we take Aristotle's theory literally, that means that the rock's motion would effectively stop its motion entirely and then start falling naturally under gravity. And if you've ever thrown an object in your life, odds are that's not what you saw happen. In fact, generally, when something is thrown, it continues moving onwards, even though the person's hand is not physically pushing that object to the side anymore. So the big question was raised then, what maintains the motion of a stone after it's left the thrower's hand, after that mover has ceased moving the object? And Aristotle did try to come up with an explanation for this. He stated that the initial violent force would transfer to the air around the object. Then the air would be capable of applying a force pushing the rock forward. And then as the rock moves forward, that force also transfers to the air around the rock in its new location. And then that air would push the rock forward, and so on and so forth. And so the air would be responsible for propelling this rock forward after it is left to the thrower's hand. So if you imagine like a bow and arrow, and in this case, the mover would be the bowstring, like launching the arrow initially. The idea is that after the air leaves the contact with the bowstring, that force has since been transferred to the air around the arrow, and the air is now what is supplying the force pushing that arrow forward. Now, at this point, you might be sitting back and thinking, I can think of at least a few problems with that. And there were many other people who agreed with you even back then. And so Aristotle's theory was a pretty decent launching point, and at least he did his best to try and explain away any flaws in the reasoning, which he was aware that there were many flaws still. And so the big problem now was, well, air doesn't speed things up. In fact, if you've ever tried to throw like a leaf or something, it tends to do the opposite. Air tends to slow things down. So air, if anything, is being an opponent to the process of an object keeping its motion forwards. And so to explain that problem, over the centuries, a lot of different people tried to come up with like different rephrasings of Aristotle's theory that addressed a lot of these main issues. And the first major one was John Philoponus over here, who developed this theory probably a little over 1,000 years after Aristotle's works came out. So it took a while. Philoponus said that an object receives motive power, which provides the external force that's necessary for this motion. So the motive power would be given to the object by whoever the mover is, and then that motive power effectively becomes a natural force. It becomes an internal source of force that allows the object to maintain its motion horizontally. He did also say, however, that this power does decrease naturally over time. So this could have been just a wild conjecture. It also could have been because Philoponus disagreed with the notion that air existed, which was a thing. So this at least explained away how an object could keep moving without necessarily needing to account for the fact that the thing that normally resists stuff is helping it forward. Now, a couple hundred years later, around the Islamic Golden Age, there was another scientist, Avicenna or Ibn Sina. This was around the time that the scientific method was being developed, so claims were starting to be able to be a lot more justifiable with evidence. And Ibn Sina said that a moving object shouldn't necessarily have to be driven by a force. What if a force and motion were two separate things, which was kind of a wild idea. Instead, he said that it would be driven by something's inclination, or mayel, which was given to it. And the inclination that's given to this object stays constant unless acted upon by an outside force. So this started to get us a lot closer to the idea now of Newton's first law of inertia, in which an object can simply maintain its motion with some quantity without necessarily having to be pushed along by an active force. In fact, a force and motion should be two separate things. So Ibn Sina kind of kickstarted this new realm of thought into how motion and force could be caused by two separate things. And we kind of kept it at that for a couple hundred years. But eventually, people started to notice that while we had a pretty good idea of the motion of things, there was a little bit more involved in the motion, especially if things were interacting. For instance, people started noticing that, well, even though two things could be moving with the same speed, if they had different size, weight, mass, heft, heaviness, whatever they were using to describe it at the time, generally those two objects would have a different impact, so to speak, relative to objects that would have like the same amount of motion and the same heft or weight. And so some scientists a couple hundred years later tried to include the heaviness or the heft or the size of objects into what we were considering to be a quantity of motion. And so like a question that was kind of posed in general was like, why would something like a moving pebble have less impact than a boulder moving at the same speed, if they were both moving at the same speed, considering that both would have the same amount of motive power or inclination, so to speak. So this kind of developed something called impetus theory, which was introduced by this fellow over here, Jean Buridan, around the 1300s. And Buridan stated that a moving object is, when it is thrown or something, is given a certain impetus force. And this impetus force can be calculated roughly according to the object's weight times its speed, whatever that may be. Buridan stated that this force, so he did claim it was a force, was internal to the object, kind of like what Philoponus was saying, and this thing would remain if it was not resisted, kind of taking upon what Ibn Sina was saying about how it wouldn't necessarily dissipate. He was also very confident in his claim, and he said that everyone else was wrong, which, more power to him. So this starts to get us a little closer to what you might think of as momentum. In fact, now we're getting to quantities that are almost directly responsible for how momentum developed. And one further contribution to that was about a couple hundred years later, again, with René Descartes, a famous philosopher responsible for a lot more than just physics again. And he stated that a moving object has a certain quantity of motion, which is the product of that object's size as well as its speed. And he also gave a concrete example here, saying that if object X is twice the size of object Y, and it's moving half as fast as object Y, then both objects would he claimed to have the same quantity of motion, effectively saying that these objects would have the same impact if they were both to like hit someone, for instance. Okay, and overall, all of these developments were taken and compiled into one theory by someone who published a very important book around the late 1600s. And that was Isaac Newton. Now, Isaac Newton took a lot of these developments, a lot of these concepts, a lot of these ideas that people were posing and developing over thousands of years, and he developed his laws of motion in terms of this quantity of motion, what he called a quantitas motus, which he would later be defined as momentum, and he claimed it was a product of mass and velocity. So Isaac Newton's definition of momentum as a vector quantity was momentum equals mass times velocity, where in this case, the direction of the momentum vector was directly inherited by whatever the direction of the velocity vector that object had. When he put that into his second law of motion, he stated that effectively a change in an object's momentum was directly the result of a force that was impressed upon that object. Or in other words, a force was equal to a change in momentum over a certain interval of time. Now, the main distinction that Newton made here was that there was a distinction between mass and whatever people were throwing around before that, like weight or size, which were all very vague and inconsistent quantities. Keep in mind that Newton was also developing the theory of gravity alongside this. And so the fact that he was privy to how gravity could be a separate thing from the mass or the amount of matter in an object gave him a big leg up on how right this theory would be going forward. And Newton's definition of all of this stuff kind of stuck over time, mostly because his Principia that was published, including all of this stuff and his laws of motion, were just so revolutionary and so well thought out and put together at the time that really people just kind of took those concepts and ran with them. And as such, his definitions are still around today. So a big idea here is that momentum is a mass times a velocity, and Newton's second law directly shows us that a force is equal to a change in momentum over time. So on to actual momentum here. The modern sense keeps it, again, the definition pretty much the same. And I have two different objects here, and I have made their mass proportional to their size here, but again, because of density, that's not always the case. Say both of these objects have a momentum of 3 kilograms per second, which is going to be the unit for momentum. Well, if this object here has a mass of 1 kilogram, and this object over here has a mass of 3 kilograms, then their speeds are going to be proportional, such that both objects have the same momentum. So in this case, a lighter object in terms of mass is allowed to have a higher speed for the same momentum as an object that has a higher mass and a lower speed as a result. So again, there's this little trade-off going between quantity of motion. And Descartes, all the way back, would say that both of these objects have the same quantity of motion or momentum. So just some general information about momentum here. Generally, the common SI units that I'm going to be using are going to be either kilogram meters per second or newtons times seconds. And we'll get to exactly where newton seconds as a unit comes into play later on. Now, the direction of momentum is going to be always the same as the direction of its velocity. That's given through the notation up here, but just remember that the only other part of momentum is mass, and because mass is a scalar quantity, it's directionless, the direction can only come from velocity. And finally, Newton did kind of include a lot of this stuff into his first law as well, saying that like an object's momentum is going to remain constant unless a force acts on said object, in which case its momentum will change as given by this definition over here for Newton's second law. Okay, so at this point, you might be wondering how exactly we get from the momentum definition of Newton's second law, the OG, to our modern definition of Newton's second law, which is force equals mass times acceleration. So we're going to start by just writing out that thing again, and you can keep in mind express it in terms of infinitesimals like dp over dt, or you could express it in the delta form if you're dealing with larger intervals that are constant. So we're going to do a quick derivation here, and I'm going to use the infinitesimal form here, just get a little bit of calculus under our belts. And so the first thing we're going to do is I'm going to take this original formula right here and sub in our definition of momentum, which is mass times velocity over here. So this becomes the derivative of mass times velocity with respect to time. Now at this point, because mass is a constant value, it's a scalar quantity, or at least we'll assume it to be such, we can pull that out of the derivative that we were taking over here. And we're left with the derivative of velocity with respect to time. And by definition, the derivative of velocity with respect to time is acceleration. And so directly we can get from this form over to the mass times acceleration form relatively easily. Now, the destination is cool, but it's the journey that turns out to be a lot more useful. Because we can move around all of these terms, we can start arranging time and force and mass and acceleration into different locations. That gives us some more helpful relationships that we can work with. So again, I'm going to start with the delta form over here, delta p over delta t, and say we were to multiply that delta t over to the other side, like here, then we'll say that the force times the time interval under which it's applied is equivalent to the change in momentum of that object. And so we can expand that out a little further, because a change in momentum would just be mvf minus mvi, or mv final minus mv initial. And through this, we get a very helpful theorem for safety and just generally figuring out the motion of objects under forces over times. And that theory is the impulse momentum theorem. So first, we have a term here, impulse, which is generally denoted by capital J. It's a vector quantity, and it's equal to the product of the force on a system with the time that it's applied. Now, there are a lot of ways that you can state impulse based on the math that we just did or the definition that I gave just now. And keep in mind that this is an impulse as a result of a constant force. We'll be giving the changing force version later on. So impulse, big J, is equal to, again, the force on a system with the time that it's applied. So that would be F times delta T. Here it would be an average force, assuming that it is a changing force, but we don't use our math techniques here yet. Impulse is also equal to the change in momentum as we just found. This formula here was what we derived on the previous slide. And then it is also equal to, again, mvf minus mvi, the change in momentum, final minus initial. So all of these can be considered to be impulse, and all of these are strategies with which you can calculate that and relate all of these different equations together. So it's a lot of equations to remember, but if you start with Newton's second law, you can get all of the different expressions relatively easily. Now again, as Newton said, an impulse is going to cause a change in momentum of that object, because if a force is exerted on that object, then it's going to accelerate by Newton's second law. And because it's accelerating, its velocity ought to be changing, and as such, its momentum will be changing as well. So again, the impulse momentum theorem is really just Newton's second law, but moved around a little bit. Now, conceptually, one of the big things that impulse momentum theorem is used for is safety implications, like impacts with car crashes or eggs falling on concrete. And there's a big misconception with that I want to address, which is that impulse alone does not necessarily impact, or no pun intended, affect how hard an impact is. And by hard impact, I mean like a object going into a brick wall, as opposed to maybe, somebody punching a pillow, for instance. So to start, I'm going to suppose that we have two eggs that are dropped from the same height. And if they're dropped from the same height, then the same amount of potential is going to convert into the same amount of kinetic energy, so they will both land with the same velocity v. Now, if both land and come to rest, then they're both going to have the same impulse by definition, because they end with the same final velocity and they start with the same initial velocity, and so their change of momentum will be the same. They will have the same impulse. So the main difference that we're going to have is that one egg is going to land on concrete, in which it's going to stop pretty much instantly, because the concrete has no give. It's not really going to, ease the egg into a stop. So in that case, the impulse is some arbitrary value that we'll just set, and the stop time is going to be relatively small, and the font sizes here are very intentional. So it has this amount of impulse and a very small amount of stop time. And so in order to work all of this out by our definition of impulse, there has to be a very large force that is exerted on the egg to make it come to a stop in this small amount of time. And so the egg will feel this really high force as a really hard hit, and the egg will probably shatter because its eggshell likely cannot withstand whatever this high force is. Now, the other egg is going to be dropped on a trampoline or like a bed sheet or a bunch of pillows, something really soft. And this is going to allow the egg to stop gradually over time. So its delta t is going to be much larger. Now, in that case, because our delta t is larger, for the same amount of impulse, our force doesn't have to necessarily be as large. It has more time to exert a smaller value of force to allow this egg to come to a stop. And because of that, this egg is going to feel a much smaller force. It'll feel less of an impact, so to speak. And the egg will likely not shatter if the trampoline is soft enough. So the big idea here is that it's impulse that doesn't necessarily impact how hard an impact is. For a certain impulse, it's more so the time of impact that affects things, where more time of impact is going to generally mean less force applied, or vice versa. So like in a car crash, you want your car to crumple so that your car has more time to come to a stop, and that means less force exerted on you as a driver. So for the impulse momentum theorem, there are a couple of strategies, because sometimes these problems can be very systematic, but it does involve a lot of steps that including vectors and calculating a lot of things based on equations that you might not have on your formula sheet. So say we have two momentum vectors like these, and we just need to figure out the change between them, the impulse. Well, the first thing I recommend you do is always calculate the initial and final momenta first. So that would just be mass times velocity for whatever you're given. And if those vectors are at angles like these are, then you should find the x and y components of each momentum vector as well. Because again, you cannot add these vectors if they're not parallel or perpendicular to each other. So the first thing we're going to do is calculate the components of P initial. So I'm going to use the vector form for this, as well as the example we'll be jumping into in a second. And so in parentheses vector form here, just note that by convention, normally we're going to be using the angle with respect to the horizontal. So pi cosine theta is going to be pi x, and pi sine theta is going to be pi y, and that would be split into these components right here. Then we'll do the same thing for pf, where again, it's the same relationships, so largely you're just splitting these momentum components into x and y components. After that, you need to find the total change in momentum delta p generally. It's not ever going to just ask you to find the components of the momentum itself. And so for that, to find delta p, generally you need to subtract the x component of final minus the x component initial from each other, and do the same thing for the y direction as well. And if you do that, you will find two new perpendicular components of our delta p, our change in momentum vector. And after that, in order to get the change in momentum, you would use the Pythagorean theorem to resolve those two perpendicular vectors together into one hypotenuse. And if you wanted to find the angle, the direction, you would use inverse tangent generally to get that angle with respect to the horizontal. After that, say the problem asks you to find like the average force or the time interval or whatever you have based on the information you have. Just remember that at the very end, your victory lap is this equation right here, where most of the hard work has been done, and you generally just need to divide one quantity by another. And that would be this equation right here. Okay, it sounds like a lot, and we're gonna do an example really quick that just kind of shows how some of this stuff is put into action. Let's see. Putting some of this stuff into practice, we've got a baseball/bat collision where the velocity of this 0.15 kilogram baseball is shown in this picture over here before and after the collision. And our first task is to figure out the impulse on the ball with both its magnitude and its direction. So I'm assuming there's going to be some vector stuff in this. Now up front, because momentum is a vector, there are a lot of ways that you can denote how it's represented as a vector. I'm up here going to clarify what notation I'm going to be using, where I'm going to say that a momentum generally is represented in parentheses form as px, comma py. And if we wanted to calculate those outright, just to speed up our math a little bit, generally that's going to be p times cosine of theta, where I'll assume that theta is with respect to the horizontal. And then our y component will be p times sine of theta over here. And in general, just helpful to remember is that momentum itself is the product of mass with velocity. So if we already have a mass and we already have a velocity, we can calculate this vector quantity outright and then split it into components later. So up front, if we want to find the impulse, again, the first step that I recommend you always start with is to find its to find the initial and final momentum first. So first is P initial, and in general, it's going to be a mass, so 0.15 kilograms for this ball, times whatever initial velocity we have, which is 39 meters per second. And so our initial momentum here is going to turn out to be about 5.9 Newton seconds. And no, I'm not really including direction here, but we can say that it is traveling to the left initially, which is helpful for us later when splitting into components. So we could then go ahead and split this into its components, wherein it's all horizontal. There's no vertical component for this initial momentum. So we can say that maybe this initial momentum is given by negative 5.9 Newton seconds in the x direction, comma 0 Newton seconds in the y direction. And that will be our initial momentum. Now we'll do the same thing for the final momentum. So down here, final momentum is again equal to a mass, so 0.15 kilograms, times our final velocity, which is 45 meters per second. Zoom in. And this is going to amount to about 6.8 Newton seconds, this time going up and to the right. So in this one, we will have both a y and x component. So solving those, we're going to say that our x component here is 6.8 times cosine of 30, comma 6.8 times sine of 30, close parentheses. And so our momentum vector here is going to be represented by 5.9 in the x direction and 3.4, color coding, whoops, and 3.4 in the y direction. Okay, oh, again, color coding, whoops. Okay, now that we have our initial and final momentum vectors, our math is going to be a heck of a lot easier, because now we just need to do some simple addition and a little bit of trig at the end. So our change in momentum vector, delta p, is comprised of really just our final momentum vector, whatever that may be, minus whatever our initial momentum vector components are. And the nice thing about using parentheses form is that you can kind of do all of that in one line. So I'm just going to subtract the x's from the x's and the y's from the y's. And so we'll take our final momentum vector, 5.9 in the x direction, and subtract negative 5.9 from that. Like that. Then it's going to be comma, and then in the y direction, things are a lot easier. It's going to be 3.4 Newton seconds minus 0, and how all of those subtract together gives us our result. So down here, our impulse in the x direction is really just 5.9 times 2, so that will amount to 11.8 in the x direction. And in the y direction, the 0 doesn't really do anything, so we will just end up with a change of momentum of 3.4 in the y direction. And so that, in a nutshell, is our change of momentum vector. But of course, we can find the magnitude. So let's go ahead and do that. So our change of momentum, delta p, overall, as a vector, or as a magnitude, is just going to be the Pythagorean theorem of these two components. So we'll do 11.8 squared plus 3.4 squared. And if we run the numbers on that, we'll get a change in momentum of about 12.3 Newton seconds overall. So that, in a nutshell, is the magnitude of our impulse. However, we did need also to find the direction. So down here, we're just going to say that the angle theta is the inverse tangent of, generally, if you want to find the angle with the horizontal, it's going to be y over x. So we will do 3.4 divided by 11.8. And the inverse tangent of those two components are going to be about 16 degrees above the horizontal when all is said and done. All right. So that's really the hard part done. Now we move on to part B, where we need to find the impact time for the collision. We need to find the average force. I should have read the question a bit more. That acts on the ball. So if we know that the impact time for the collision is about 1.2 milliseconds, we need to find the average force. 1.2 milliseconds is really short. So this is going to be a pretty high force based on this momentum over here. So our equation here is going to relate the force average and the impact time, delta t, with the change in momentum that this ball experienced over time. So to do that, if we want to find average force, really we just need to take our delta p and divide it by whatever our change in time was. So here, our change in momentum was 12.3 Newton seconds, and we're dividing that by effectively 1.2 divided by 1,000. And if we run the numbers on that, we will get our average force, which is, wow, a whopping 10,250 newtons on average during that collision. That is crazy. So if you know a baseball player, they're putting in some work moving these balls. All right. And then finally, I guess because force is technically a vector quantity, we can include a direction with that. And the direction is always going to inherit the direction of the change in momentum. So the angle theta here will be 16 degrees above the horizontal, just like the impulse. All right, and that is a pretty standard impulse problem. Okay, so that's all well and good with forces that are constant or that we can just find on average. But what if we wanted to find the impulse due to changing or variable forces? Well, first off, I'm going to start with these fellows right here. These are two very different looking graphs, although they are both kind of mound-like. And the big idea with a changing force, especially if you have a graph, is that the area between the line of a force versus time graph and the horizontal axis is going to give you impulse. The explanation for this is very similar to how we would justify the work done due to a force versus displacement graph, or the displacement due to a velocity versus time graph. Generally, it's just that if you have a constant force acting over a certain interval of time, the graph for that is going to end up looking like a rectangle. And if you find the area of that rectangle, you will be finding the force times the interval of time, which gives you the impulse. And it just so happens that the area works itself out that way in every other case as well. So generally the idea here is that the more area you have, the more impulse you're going to have. But there is more to it than just that. Because both of these graphs, surprise, surprise, have the same amount of impulse. They just have different shapes. And so if two graphs like these have the same area, generally it's going to be the flatter curves that represent the softer impacts, because this curve right here has a much lower average force, or a much lower peak force even, than this steeper curve right here, which is going to represent a harder impact with a higher maximum force. So, I mean, just looking at these, one's kind of pillow-like, one's kind of spike-like, you generally want to be in an impact that's more representative like a pillow or a mound here, as opposed to a spike. That just looks physically unpleasant. So as a little bit of practice here, we have these three different graphs here, A, B, and C. And again, we're saying that the area between the line of a force versus time graph and the horizontal axis is impulse. So with each of these three figures, we are being asked to rank the graphs according to the impulse on the body, which is the greatest first. So looking at graph A here, we have a constant force of 2 force units over a time interval of 6 time units. So if we wanted to find the area of that graph, it looks like a rectangle, so we'll just do length times width. So our width is 2f naught and our length is 6t naught, and if we multiply those together, we will get an impulse, or an area, of 12 f naught t naught. All right, there's our first one. So now graph B. With graph B over here, we have a height of 4 and a width of 4 and a length of 3. So again, it's going to be a rectangle, so 4 f naught times 3 t naught is going to give us also an area of 12 f naught t naught. Okay, so these two graphs, even though they look very different, have the same area or impulse. So finally, for graph C over here, it is represented by a right triangle, so we're going to use the formula 1/2 base times height to get its area. Its height is 2 f naught, and its base is 12 t naught. And if we resolve this, well, surprise, surprise, the area, or the impulse of this graph, is also 12 f naught t naught. So all three of these graphs have the same area or the same impulse, even though they represent very different types of collisions. So the answer here is that they all have the same impulse. But if we were to think about the impacts that each of these would experience, the one I would not want to be in, or the one I'd want to be in the least, is probably graph B here, because it represents the hardest impact that happens over the shortest amount of time. So it's more of a punch as opposed to a gentle shove that maybe the others would be. Okay, so again, just know that force and time have as much to play in an impact as the overall impulse or change in momentum does. And because we're using areas to determine the impulse on graphs like these, the area under a curve is a very good sign that we can also use an integral to figure out impulse. And so when net force is changing, generally impulse is going to be the integral of net force with respect to time, given by this form right here. So impulse, big J, is equal to the integral from time initial to time final of force with respect to dt, and that'll give us a change of momentum, delta p, or any of the other ways that we expressed that previously. So this is especially useful for evaluating force curves, such as these little lumps over here, which are really common. And so generally, if you can get a quadratic expression for a curve like this, the integral is the way to go for figuring out impulse. And because we can say that the antiderivative of force with respect to time is momentum, we can also say that the derivative of momentum with respect to time is force. Again, wherever there's an antiderivative, there is a derivative in the opposite direction. And this takes us all the way back, believe it or not, to Newton's second law, where we started, where the slope or the derivative of momentum is equal to force. As Newton said it, force is equal to a change in momentum with respect to time, dp over dt, all right? And if you have a constant line on any momentum versus time graph, you can also interpret this as the slope of that line. So just change in y over change in x, all right? So we're gonna do one more example involving a little bit of calculus, and then we will call it a day on momentum and impulse. Let's see what we got. Right here, we've got ourselves a calculus problem. We have a collision represented over here with a wall that lasts from 0 to 2 seconds, and the force acting on this 2 kilogram object, so we have a mass, varies with time, given by the equation negative 4t squared plus 8t, and it's all going in the I direction here. So part A, as always, has us generally find the impulse imparted on the object during this collision up front. And again, just like with the previous example, this tends to be the lengthiest part of the problem. Everything else goes pretty quick. So here, because we have a function for force, we have a changing force, we should be using the integral form of impulse here. So I'm going to write that out first. Our impulse, big J, is equal to the integral of our force function with respect to time. So expanding all of that out and including our bounds, we know that this impact happens between 0 and 2 seconds. So our bounds will be from 0 to 2. And plugging in for our force function here is negative 4t squared plus 8t. And we're integrating that function with respect to dt. Now first, taking the antiderivative, we're going to end up with the integral of negative 4t squared. So that'll be negative 4/3 times t cubed, raising the power and then dividing by that new power. And then we're adding to that the antiderivative of 8t, which is going to be 8 divided by 2 times t squared. So 4 times t squared. Now outside the brackets, I still need to include our bounds so that we remember to do the fundamental theorem of calculus here. And that's just going to involve plugging in 2 here, because if we plug in 0 to any of these terms, they're all just going to go away. So here it will be negative 4/3 times 2 cubed, which is 8, plus 4 times 2 squared, which is 4. So if we run the numbers on that, we will find that our impulse for this collision amounts to 5.3 Newton seconds. That is our answer for this one. And again, really, in most of these problems, that turns out to be the hard part. And the rest is just remembering all the other different forms that we can express impulse in terms of. For instance, if we then try to figure out what the average force acting on that object was, well, a very easy way to do that is to then take this value of impulse and divide it by the total time that it took, as opposed to doing any crazy calculus stuff. So average force generally is included in the simplest form of impulse, which is force times time equals our big J over here. So average force then is going to be equal to our impulse, J, divided by delta T. We know that J is 5.3 Newton seconds from up above, and the total time of the collision was 2 seconds. So our average force here is going to be 5.3 divided by 2, which is 2.7 newtons. And we could say that's to the right, because we know that this force is all acting in the horizontal direction, and it's a positive impulse. All right? Well, beans. Finally, part C here has us figure out what this object's final velocity was if it started from rest. So again, this is another way that we can express impulse, because impulse would be a change in momentum. So mvf minus mv initial. So final minus initial momentum. And because we know that this object started from rest, we can go ahead and cancel out this term to 0 because its initial velocity is 0. So here our goal is to figure out vf, final velocity. So we already know what impulse is. It's 5.3 Newton seconds, and that's equal to the mass of this object, which was 2 kilograms from up above, times vf. So again, vf is going to equal 5.3 divided by 2, which turns out to be exactly the same as the average force that we had over here. Really just a coincidence. That doesn't always happen. But here our final velocity will be 2.7 meters per second, also to the right, because it is being pushed to the right. So this is our answer right here. Cool. So besides the scary calculus stuff, really not too bad. And as long as you remember all these different forms of impulse, generally these problems are just jumping through hoops in different orders. So that is about it for momentum and impulse. Anything else really is just some variation of any of the examples or concepts that we covered here. So I hope this video helped. I hope you found maybe some of the history stuff interesting if you stuck through that. And with that, I will catch you on the next video over collisions and conservation of momentum. Peace.